Hello everyone and welcome to the video for section 1.2 where we're looking at graphs of functions. The skill objectives for this particular video are 1, to go and classify functions as even, odd, or neither. Number 2, determine if a function is increasing, decreasing, or constant. Number 3, calculate the average rate of change. Number 4, evaluate a difference quotient for a function. And number 5, graph piecewise defined functions and work with those. The conceptual objectives: identify common functions. Number 2, develop and graph piecewise functions. Number 3, understand symmetry properties of even and odd functions. And 4, understand the difference quotient is an average rate of change. Let's first take a look at the different common functions. These are some common functions that are out there. And in terms of these, you should know the basic shape and the basic equation with those. Later on, we'll deal with some transformations, and you'll start looking at transformations on these common functions. So you really want to know the equation, but you should also know the basic shape. So when you hear those, when they start talking about a cube function, you have an image of what that is. Or when they talk about an absolute value, an image of what that looks like. So the first function we have here is the constant function, where y equals a constant value. It's just going to be a horizontal line. Then we have the line y equals x. That's also called the identity function. The square function is parabola, y equals x squared. And the cube function is where you have y equals x cubed. And it has this shape here. The next one you have down over here is the square root function. Y equals the square root of x. Has that shape. Notice that square root just stops there. We don't, because we can't go into the negative values. There's no real value there, no real answer when x is negative. But the cube function does have values when x is negative and when x is positive. So that's going to be true for any, actually any odd root is going to have something very similar to that, and any even root is going to have something similar to the square function. And then we have the absolute value function, has this V shape. That's a very characteristic or distinct characteristic of an absolute value function, is it's going to have that sharp point. When you see graphs where you see that sharp point, a lot of times that's going to be because they deal with an absolute value. And then the other one we have is the reciprocal function, which is y equals 1 over x. You've graphed this before. It has vertical asymptote. Here at the y-axis is a vertical asymptote, and the x-axis is a horizontal asymptote. So the function starts very high up, close to the y-axis. It comes down and just gets very, very close, but never crosses the x-axis as you go in both directions. Now that we've seen those common functions, another thing we have to look at in terms of classifying functions is whether or not it's an even function or an odd function. These functions, even and odd functions, have some very nice properties that can help make using these functions easy to work with. And what you have graphically, when a function is even, it's going to be symmetric to the y-axis. In other words, if you fold that graph over the y-axis, what's to the left of the y-axis would land on top of what's to the right of the y-axis. An odd function is symmetric about the origin. So what happens there, some people think of that when we're symmetric about the origin, some people think of it as a double flip. Take the part that's to the right of the y-axis, you flip it over the y-axis and flip it over the x-axis, or flip it over the x-axis and the y-axis. Either way, flip it over both axes, and you'll get the one part will land on top of the other one. Another way of looking at that is a rotational symmetry. The idea that if you graph an odd function, if you look at that graph and you turn the graph, physically turn the graph upside down, it will look the same. You can kind of see these in two functions. An even function would be the square function, and an odd function would be the cube function. So if you want, pause the video, take a look at those graphs. Look and see the symmetry over the y-axis for the square function, and look at the odd function, the cube function, as being an odd function. Look at it in terms of the flipping it over the y-axis and x-axis, or the rotational part. Okay, now let's take a look and let's talk about the algebraic test. in terms of determining if a function is even or odd. And really the key part of that algebraic test is going through, we're going to have f of x, you're going to want to find f of negative x, or the opposite of x, and simplify that. So what you're really going to do when you find this, you're going to replace the variable with the opposite of x, with a negative x. All the x's are going to be replaced with an opposite of x, or negative x. And you're going to simplify that. And really one of three things can happen. One of three things can happen. Either when you put that in there and simplify it, if you get back to what you started out with, then we know f of x is an even function. We can sit there and say, okay, this function is even. If when you do that, you don't get back to what you started out with, but every sign in the problem is opposite of what you started out with. In other words, that this right here simplifies to be the opposite of f of x itself, then we can say f of x is odd. Now, a fast way to check that one is once you do the f of negative x, you go through it, doesn't come out to be the same. In your mind, multiply that result by a -1. If that gets you back to what you started, then you know it's odd. If not, if it's not even and it's not odd, then it's neither. So really what you want to do, once you go through and you say, okay, it's not the same thing, it's not exact opposite, you really know that the answer is that it is neither. You don't have to worry about double checking all of that. Let's take a look at a couple examples. In this first example, I want my f of x is x squared minus 2. And so what I'm going to do, what I did is I replaced f of the opposite of x. I put negative x in for the variable, so I have the opposite of x squared minus 2. Now when I square that, it's going to give me x squared minus 2, which that's what I started out with, so I know this is even. Let's look at function g. G of x is x cubed minus 3x. So g of the opposite of x, I replaced all the variables with a negative x, or opposite of x. And I take the opposite of x to the third power. Well, that's going to come out to be a negative x cubed when I multiply it out. And negative 3, or minus 3, times the opposite of x will become out of positive at 3x. So I look at that and I say, oh, if I go through and look at that, I can pull out a factor of -1. So I have -1 times x cubed minus 3x. And x cubed minus 3x is what we started with. So therefore, because when I pulled the -1 out, this is what I started with, I know that g of x happens to be an odd function. Now let's take a look at number 3. So we had an even, we had an odd, and you can see right here, here's a neither. So this is what happens. I replace the variable with the opposite of x. So I got the opposite of x squared plus the opposite of x minus 2. Now when I square that, that's going to be a positive x squared minus x minus 2. That's not what I started out with. And if I pull out a factor of -1 from this, I get -1 times the negative x squared plus x plus 2. That also is not what I started out with. So since neither of these here and here are what is equal to h of x, I know h of x is neither even nor odd. Another classification we have is if a function is increasing or decreasing, or if it's constant. If it's constant, it's going to have a portion of the graph that will be a horizontal line. Most of the curves when you're dealing with a curve, you're not going to have necessarily a constant portion. Sometimes you could, but for the most part, it will be increasing, decreasing when you're working with that. So when you look at that graph, if you see a straight line portion, then we can say that portion is constant, and where you can enter those points. But for our purposes right now, what you have to remember on this one, I always tell people, in terms of identifying increasing and decreasing functions, you read a function like you read a book. You go from left to right. When you go from left to right, as you move from left to right, the function values are going up, or the graph is going up, then it's increasing. So here, at this point here, when I look all at the portion of the graph going from negative infinity to a on this one. As I move from left to right, and imagine like a vertical line going here. As I move from left to right, I can see that this function graphically is going up. So therefore, I know on this particular problem that this is increasing. This one is increasing on the interval from negative infinity to a. And we'll just, whenever you're talking about increasing or decreasing functions, always use an open interval. Always use parentheses when you're talking about when it's increasing or decreasing. Now let's look from A to B. As I go from A to B on here, you can see as I move from A to B along the x-axis, my graph is going down. So in this case, this is going to be decreasing from, on the interval, from A to B. The next one I have is B to C. As I go from B to C along the x-axis, you can see that the graph is going up. And so therefore, when I go from, this is also increasing, so I'll do a union here with the interval from B to C. And then decreasing from C to positive infinity, it is decreasing, so it's going to be union C to infinity. So this is, again, you're doing this by just taking a look at the graph as you go from left to right. Is it going up? Is it going down? Don't be concerned. Some people get worked up because of these arrows here and here, and it's specifically this arrow here because they look at that as pointing down. What that means is that when you see the arrows, it means that the graph continues in that basic way. It just continues like that. But again, when you're reading a function, I'm not concerned about these arrows and this arrow. I'm concerned about starting from the left and going right and what is happening as I move from left to right. Now, another thing that we have when we work with a function, or when we've worked with functions in the past, you've had this thing called an average rate of change, okay? And you actually have dealt with this quite a bit. The average rate of change, when you're dealing with a linear function, the average rate of change happens to be the slope. It's the slope formula. Change in y over change in x. And that's really what an average rate of change is. It's where you identify 2 points and imagine a line connecting those 2 points and finding the slope of that line that connects those 2 points. So what you're going to see on this, we have a function f of x, and the average rate of change of f of x, we want to find the average rate of change of f of x on an interval. This is a closed interval from whatever x1 is to x2. And that average rate of change is going to be f of x2, so plug x2 in for x, that gives us f of x2, minus f of x1 over x2 minus x1. Let's look at an example here. In this case, we have f of x is equal to x cubed minus 2x. And we want to find the average rate of change on the interval from -1 to 2. So I go through and find, first thing I have to do is find f of -1. So f of -1, I put -1 in for x, I get -1 cubed minus 2 times -1, which is -1 plus 2, which equals 1. So f of -1 is equal to 1. Now I'll have to do f of 2. F of 2 is going to be 2 cubed minus 2 times 2. 2 to the third is 8 minus 4, and the result there is 4. So I know f of 2 is 4. So I want to find the average rate of change from on the interval from -1 to 2. So I know that's going to be f of 2 minus f of -1 over 2 minus a -1. And f of 2 is 4. F of -1 is 1. So I get 4 minus 1 over 2 minus a -1 would be 2 plus 1, which gives me 3 over 3, which equals 1. So if I was to draw a line that connected the points -1, 1 to the point 2, 4, that line is going to have a slope of 1. You always want to remember that the average rate of change and the slope, doing a slope formula, mean the same thing. That's going to be something that's key as you're working forward with this. Now we get to the difference quotient. The difference quotient, as I will sit there and say, and I firmly believe this, is probably, in terms of what we do in this class, in terms of where it leads, the difference quotient is probably the most important thing mathematically in the development of mathematics. It's probably the most important thing that we deal with in this class, and it comes very early. And really what the difference quotient, there's two branches of calculus. You have integral calculus and differential calculus. The difference quotient really is the basis for what is the branch of that's called the differential calculus. Now what's happening here? The difference quotient, what we're really looking at is on this thing, you'll notice this curve in blue. That's y equals f of x. And I've labeled 2 points. Here's x, at x, we have that point on the curve, and the coordinates are f, x, f of x. And over here we move h units over, so I have x plus h, and it comes up here, and the coordinates of that point are x plus h, f of x plus h. And what I've done is I've drawn a line through those 2 points. And really what the difference quotient is really the slope of this line. We're going to find that slope of that line. So really what we're going to do to find that slope, we look at what's called the average rate of change. And so the average rate of change as I go from this point here to that one is going to be f of x plus h minus f of x all over x plus h minus x. And if you simplify that, you get f of x plus h minus f of x, that whole thing over h. Now, like I said, this idea here leads us to differential calculus. It adds in one more piece that we might get to at the end of the year, or for sure you'll deal with in a calculus class. And the idea is looking at how the value of this difference quotient changes as h gets smaller and smaller. That's really where differential calculus goes. But your job is going to be to evaluate these difference quotients. You're going to go through, find f of x plus h, subtract f of x, divide by h, and your goal is to get an expression that it will be equal to. Let's take a look at an example. In this case, our function is f of x is equal to x squared plus 3x, and I want to find our difference quotient, f of x plus h minus f of x over h. So the first thing I have to do when I'm working on this is I have to find out what f of x plus h is. I already know what f of x is. It's x squared plus 3x, and that's going to end up going here. But I got to find out what f of x plus h is. So I came over here, f of x plus h equals x plus h squared plus 3 times x plus h. Now you have to remember right here, x plus h squared is x plus h times x plus h. So you're going to have to FOIL that out. And when you FOIL that out, you'll get x squared plus 2xh plus h squared. I distribute the 3, I get plus 3x plus 3h. So therefore, I know f of x plus h is equal to this expression right here. X squared plus 2xh plus h squared plus 3x plus 3h. And once I have that, I now know, because right here, I have to evaluate f of x plus h. I have to do f of x plus h minus f of x over h. So I'm going to replace f of x plus h with this expression. That's right here. Minus f of x, which is x squared plus 3x. Please notice I put parentheses around f of x in this case, and you're going to want to do that because you're subtracting f of x, which means that is going to have to be distributed to every term of f of x. So this, when you do the distribution there, that becomes x squared plus 2xh plus h squared plus 3x plus 3h minus the x squared minus 3x over h. Now here's where we have some good things that happen. Because what happens at this point, you'll notice I have an x squared and a minus x squared. So those will cancel out. And same thing with a minus 3x and a 3x. Those drop off. When you're dealing with an f of x that's a polynomial like that, when you go through and simplify this, everything without an h should drop off of the numerator. So what I'm left with once I do that, once I simplify that, is 2xh plus h squared plus 3h over h. So now what we're going to have to do is reduce this particular fraction. And in order to reduce a fraction, you have to keep in mind, you can only eliminate, when you reduce a fraction, you're eliminating a common factor, not a term or part of terms. So what that means is I have to look at this. I know that when I reduce this, I'm going to eliminate a common factor. So I'm going to have to go and pull out a factor out of the numerator, which in this case, my common factor for the numerator is h. So when I pull an h out, I'll be left with 2x plus h plus 3 over h. At this point right here, this is where I can now go and cross off those h's. They drop off. And so my final answer on this, in terms of the difference quotient, is going to be 2x plus h plus 3. That would be the final answer that we get. I know it doesn't necessarily look great, but that's as far as you need to go. And that would be the correct answer on this particular problem. Now, the last thing we need to do is deal with what are called piecewise functions, or functions that are defined in pieces. In this case, you'll notice I have f of x is equal to x squared minus 3x when x is less than or equal to 2, and it's equal to 2x minus 3 when x is greater than 2. Now, what happens with this? These pieces, right, these inequalities here, those represent the domain for each one of the pieces. So, in other words, I will only use this first piece when I'm using an x value that's less than or equal to 2. I will use this second piece, 2x minus 3, whenever I have an x value that's greater than 2. Please understand, these inequalities only are based on what value of x you're plugging it in. You're not looking at that in terms of what comes out of the function. This is only looking at the number that you're plugging in for x. Does it make this inequality true or that one? For example, let's take a look at f of negative 1. In this case, f of negative 1, I'm looking at negative 1. I know negative 1 is something that's less than or equal to 2. So f of negative 1, I'm going to plug it into the top piece, is going to be negative 1 squared minus 3 times negative 1, which when I simplify that, negative 1 squared is 1, minus 3 times negative 1 is going to be plus 3, so the result is 4. So in this case, f of negative 1 is equal to 4. F of 0. F of 0. 0 is another number that is less than or equal to 2, and so therefore when it works in this inequality, so when I find f of 0, I'm going to deal with this piece, that top piece. So f of 0 is going to be 0 squared minus 3 times 0, which is going to be 0. Now we take a look at f of 3. In terms of f of 3, now 3 is a number that's bigger than 2. So in terms of evaluating f of 3, I'm going to put it into this bottom piece. So f of 3 in this case is going to equal 2 times 3 minus 3, which is 6 minus 3, which equals 3. F of 5. F of 5 also is a number that is bigger than 2, so I plug it into that bottom piece, and I know f of 5 is going to be 2 times 5 minus 3, which is 10 minus 3, which equals 7. The one thing in terms of evaluating a piecewise function that you have to be concerned with is at the endpoint. So in this case, we're looking at f of 2. F of 2 here, we have to look which inequality does it satisfy. Now in this case, where the one that satisfies is going to be the one that has the either less than or equal to or greater than or equal to. And in this case, that's this one right here, the top piece. So f of 2 is going to equal 2 squared minus 3 times 2, which is 4 minus 6, which in this case is -2. So take a minute, pause the video, and make sure you're comfortable with how I evaluated each one of these. Again, remember, in a piecewise function, I have one that has 2 pieces here. I can come up with a function that has 3 pieces, 4 pieces, 5 pieces, whatever I want. In terms of going through and working with them, probably what you're looking at is 2 or 3 pieces right now. But keep in mind, you can go to a higher number of pieces. Now let's take a look in terms of graphing these. In terms of graphing this one, I have on this particular problem, f of x, it's in 3 pieces. F of x is the opposite of x when x is less than or equal to -1. It's equal to 2, so it's going to be constant in this case from -1 to 1. And it's just going to equal x when x is greater than 1. So I want to graph this one. Now, this is where the endpoints make a difference. Okay, you've got to always look at the endpoints here. Now, for this first piece, I use that when x is less than or equal to -1. So for this first piece, what I'm going to do is I'm going to go and put -1. I'm going to use -1 to start out with. When I put -1 into this piece, I know I'm going to get +1. And because it's a less than or equal to sign here, I know at the point -1, 1, I'm going to put a closed circle. Dot. And then what I'm going to do is, since I'm only using that first piece when I'm using values of x less than -1, I'll put -2 in there and I'll get a +2. So I get the point -2, 2, and graphically, I have that line. Now let's take a look at the second piece. And now, even though we don't include the endpoints there, I want to use those endpoints, the -1 and 1, to help me evaluate this. And we don't really have an x there. It's always going to be a 2 from -1 to 1. So the first one at -1, when I use a -1 for this one, I'm going to get 2. But since -1's not included there, at -1, 2, I'm going to have an open circle. So it's going to look like it's going to have this open circle right here. And then at the next endpoint, +1, I still will get 2. And so I'll have another open circle at that endpoint. So we put the open circle at 1, 2, and then I can connect those. So there we go. There is the second piece. The third piece, when x is greater than 1. Now notice we don't have greater than or equal to 1. 1's not included here. So for that last piece, when I put 1 into x here, because we still want to use the endpoint, I'll put 1 in. Because it's a greater than, I'm going to use an open circle. So I'll have an open circle at the point 1, 1. And then after that, at 2, we'll be up at 2. So I'll get close. And graphically, it will go off like that. That would be the graph of this particular piecewise function. Now, your calculator can also graph piecewise functions. So I will need to show you that in class next time. So with that, this does conclude our video. You've gone through, we've taken a look at the different types of functions. I know there was a lot here, but we have a lot of different types of functions and we have the graphing of those. So with that, we'll close this video and remind me to go through and show you graphing of piecewise functions on your calculator in class next time. So with that, have a good evening and we'll see you in class.